All right, we're beginning the lecture on handout number 15. This is the second lecture on dopant diffusion and profile measurement. And we're working on chapter 7 of your text. So last time we introduced some of the basics of dopant diffusion. We talked about basic definition of sheet resistance, and the scaling requires per MOSFETs. And we pointed out there's a conflict between the need for smaller series resistance and the need to decrease junction depths to improve control of the channel charge. We also talked about short channel effects and how BT decreases as L goes down. We mentioned the use of pre-deposition, either in the gas phase or by ion implantation, and then the use of subsequent drive-in of dopants to create doped regions. We spoke about macroscopic diffusion from the point of view of fixed first and second laws, and gave a few cases. There were only about 3 or 4 cases where there are simple analytic solutions to the diffusion equation. Today, I want to just briefly review those analytic solution examples, and then talk about a brief introduction to numerical solutions to the diffusion equation. Then we'll talk about design of diffuse layers based upon certain device requirements, such as the sheet resistance. And our first deviation from Fickian diffusion, we'll discuss electric field effects on dopant diffusion. So let's go on to slide number 2. And just review from last time this pictorial view of fixed second law. What I'm showing here is a volume element that is shown by the blue sort of rectangular element. And there is a flux F sub in going in the left-hand face, and a flux F sub out going out in the right-hand face. Remember, again, our basic definition of flux is it's a number of atoms or particles per unit time, per unit area. So looking at this in this cube, we can calculate the net flow of atoms into this volume, into that small volume, as shown in the upper left corner, is equal to the area A of one of those faces times the difference between F out minus F in. So that's the net flow of atoms. And we can write that as A times, and just looking at sort of the geometry, it's delta X times the change in concentration, delta C, divided by delta time, delta T. So we can just rearrange this a little bit. The A's go out, and what we see is that the first derivative of the flux, delta F over delta X, is equal to the time change, delta C over delta T. So mathematically, if we want to write this, not in terms of deltas or differences, but in terms of differentials, what we see is a time rate of change of the concentration in the box, partial C, partial T, is equal to the first derivative of the flux, partial X. And then we can substitute in the equation on the center of the page. For the flux, we know from fixed first law that F is equal to D partial C partial X. So that is indeed a way of deriving, just sort of bookkeeping, of deriving fixed second law. Now, the equation in the center of the page can be simplified somewhat if we are in a special case where the diffusivity is a constant, where it doesn't vary in space. I can pull the D out of the partial derivative with respect to X, and we just get partial C, partial T. So the time rate of change of the concentration is equal to a constant diffusivity, it's a number, times the second derivative of the concentration with respect to X. So that is, at the bottom of the page, would be then the special case of fixed second law when the diffusivity is a constant. So let's go on to slide number 3. And these are a couple of cases we solved last time, or we wrote down the solutions last time for 2 cases which are commonly encountered and for which analytic solutions are available. On the left-hand side, I'm reviewing the case of a pre-deposition. And again, by definition in this case, we are assuming that there is a supply of dopant, or atoms that are diffusing, that holds the surface concentration at a constant value, C sub S. That number is fixed. And we said in this case that the shape of the profile, C as a function of depth, X, and time, is given by this surface concentration, C sub S, times the complementary error function of X over 2 square root dt. So that is the actual analytic solution to fixed second law for a constant diffusivity. And we also know that the integral of that function integrated over space or throughout the silicon has a value q. That's the dose, so the area under the curve. And that can be solved for, and it turns out to be 2 c sub s over square root of pi times square root of dt. So this is a particular case, and we, in fact, showing a plot on the vertical axis is c over c at s as a function of depth for several different times. There are 3 curves here shown where the square root of dt, or 2 times the square root of dt, is being varied from 0.1 micron all the way up to 1 micron. You get a feel for how the shape of a complementary error function evolves with time. In contrast, on the right-hand side, we're showing the case of a drive-in that would typically be done after pre-dep. And drive-in takes place usually under the assumption of a constant dose, Q, so the constant area under the curve. And what's happening as a function of time then is that the shape of the curve is changing, and we know the solution is a Gaussian, the solution to Fick's second law. And in fact, if you look at this equation as a function of time, you'll see that the concentration of the surface is dropping as a function of time according to 1 over the square root of dt. And that the profile is broadening, its width or its standard deviation is increasing according to dt. And there are a couple of different cases shown on the right. So these solutions are valid under this particular case where the concentration of a diffusing dopant is less than n sub I. And that implies, in that case, that the diffusivity is a constant. It doesn't vary in space. We'll talk in subsequent lectures about the case when the concentration is quite high or higher than n sub I. So let's go on to slide number 4. And this reviews from last time what we showed is an Arrhenius plot of the intrinsic diffusion coefficients of some common dopants in silicon. And what we're showing on the left axis on a log scale is the diffusivity in units of centimeters squared per second. And the x-axis is 1,000 over temperature in Kelvin. The lower x-axis, the upper x-axis, actually has the temperatures actually indicated. So these are intrinsic diffusivities, so they apply when the carrier concentration of the dopant is less than Ni at the diffusion temperature. One thing you can notice right off the bat is there are some fast diffusers in silicon, such as boron, phosphorus, and indium. The upper 3 curves. And the slower diffusers are arsenic and antimony in silicon. It turns out, just for practical reasons, because of their high electrical solubility, that boron is often the p-type dopant of choice. It pretty much is. And arsenic, in n-type dopants, you can choose arsenic or phosphorus, but arsenic is usually chosen because of its higher electrical solubility, and also sometimes its lower diffusion coefficient. It's easier to control profiles. So typically we're going to have issues with controlling diffusion in p-type regions because boron is diffusing at any given temperature almost an order of magnitude higher diffusivity than the case of arsenic. All right, let's go on to slide number 5. And here what we are trying to talk about is the effect of successive diffusions in, say, a MOS process flow on the doping profiles. You remember from the first lecture of this course, we kind of walked through an example of an integrated circuit fabrication process. And you know that they involve a large number of different steps at various temperatures. We don't just simply do a pre-dip and then a drive-in and then it's done. There could be oxidations, there could be other high temperature steps in which the dopants are going to move. So if you have a whole series of steps, the question is, what is the actual final profile and how can you approximate it? Well, it turns out in the case of Gaussian diffusion that we can write the total effective D2 product as being a measure of the thermal budget that's used in that process. And for Gaussian diffusion, we can actually sum up the products of the diffusivity in any given time step times the length of that time step, d times t. We can sum up those dt products, add them up, and end up with an effective dt for the entire process. Again, assuming that in each case the diffusion satisfies the Gaussian assumptions. What we'll typically find as you go through a whole process is that some of the processing steps may be negligible. And that's because the diffusion coefficient in this formula is exponentially activated, or it varies with temperature exponentially. So the highest temperature steps in the process typically dominate. It's not always the case. For example, when we talk about transient enhanced diffusion, we'll see that's not the case. But for normal diffusion, you expect the highest temperature steps to dominate this equation. And so you can usually zoom in on those as being the ones that primarily determine the DT product and therefore the shape of the profile. One thing we have to be aware of is that this Gaussian solution we've been talking about only holds if the delta function approximation for the initial profile is reasonable. We talked about this last time. So it holds in the case where the width of the profile initially, when you start, is small compared to the final width or compared to the total DT. If that assumption is not valid, then we don't have a simple Gaussian solution necessarily. Okay, let's go on to slide number 6. And here we're going to go through some principles and examples of the design of diffuse layers. So what we want to do is, as an engineer, process engineer, or working with device engineers, we'll want to typically design a diffusion process or a pre-dep and diffusion and a dry-in process so that we end up with a certain sheet resistance that's required electrically by the device. So that's sort of the goal of this section. And I'm showing on the left-hand side just the example of a cube of silicon where the top region is colored in orange, and that is the little sheet through which we're going to be passing a current and measuring the voltage. And this little sheet has a particular geometry. What we're going to consider is the case where the length of this resistor is actually equal to its width. So it's a square, and it has dimension W by W. And so we're going to define the sheet resistance of this junction, last time we talked about it, as being the resistivity, which is an intrinsic property of the material depending on how it's doped and things, divided by xj, the junction depth. You can see xj marked on the left-hand side. And the units of that sheet resistance then are given to be ohms per square. So the sheet resistance is indeed the resistance R that you would get in a resistor made of 1 square of this material. And you can either write it as Roman R sub s or rho, the Greek letter rho sub s. And the S indicating it's for a sheet. The resistivity rho, remember, is given by 1 over Q, the electronic charge, times the carrier concentration N, times the mobility, which is in general a function of N. And the resistivity has units of ohm centimeter. Xj has units of centimeter. They cancel out, and you end up with a sheet resistance in ohms per square. That's all reasonably intuitive, assuming you have a constant doped layer. If the layer is non-uniformly doped, you need to integrate the doping profile times the mobility in order to calculate the sheet resistance. So the equation shown near the bottom of the slide says the sheet resistance can be obtained by 1 over the integral Q times the integral from 0 to the junction depth of the carrier concentration profile, N of X, or the doping profile, minus NB, where NB is the background concentration that tells you where you cut off the electron concentration. That quantity times the mobility, which is in general a function of N, dx integrated. So that's what you would do in the case of a non-uniformly doped layer, where the doping concentration is varying in thickness. Now, it turns out this equation, you can solve it yourself, but this equation has already been numerically integrated by Irwin for a couple of different analytical profiles, in particular the case of the Gaussian and the complementary error function profiles. And those the solutions to those integrals are given in your text, either in Chapter 7 or there's also an appendix where those solutions are given. So let's go on to slide number 7. And at the top of the slide, we're showing an example of Irwin's curves for the particular case of P-type Gaussian profiles in an N-type background. And what you see in these curves on the y-axis is the surface concentration, so that would be C sub S in atoms per cubic centimeter. The x-axis now is effective conductivity, and it has units of ohm centimeter to the -1. So that's the x-axis. If you just go to the bottom of the slide, thinking about it, that is the effective average conductivity. It's the inverse of the average resistivity. So we can write this as a sigma bar, and it's equal to a 1 over the product of rho sub S times xj. So it's 1 over the product of the sheet resistance times the junction depth. So there are kind of 3 key parameters we need to identify in using these curves. There's the surface concentration, which is the y-axis in the profile. There is, again, this is for a particular type. This is for a Gaussian profile. There is the sheet resistance, which is coming into this effective conductivity. That's really part of the x-axis. And there's the junction depth. So the x-axis has sheet resistance and junction depth built into it. And now the metallurgical junction is the place, the point in depth where the chemical concentration in the diffused region of the diffused dopant equals the background concentration, Cb. I will do an example shortly after this where you can see how these curves are used. But each curve, a different color, is for a different background concentration. So this basically tells you that you can take these 3 key parameters and they have a unique relationship among themselves for the particular case where the shape of the profile is known. In this case, it's Gaussian. So in fact, let's go on to slide number 8. We're going to walk through the best way to understand these Irwin's curves, just to go do an example. And what we're asked to do in this example is to calculate the drive-in conditions, which means the temperature and the time, to produce a CMOS P-well. So it's a P-type region, and it's called a P-well of a certain thickness. And what we want to do, we're told that the constraint is that the sheet resistance of that P-well should be 900 ohms per square. Okay? And it has to have a certain junction depth, which is shown schematically in the figure, xj to be 3 microns. And that xj, again, is the point where the boron concentration then will reach the background concentration, which is given by 10 to the 15th per cubic centimeter. So again, we're informing a P-well by ion implanting boron into the region onto the wafer, and the region on the left is blocked, so we're just being in one region. And typically, you would implant boron at a certain dose, say 10 to the 13th, and an energy, and then you want to drive that in, and we're interested in the driving conditions, what temperature and time will we need to get it to go that far and to have a particular sheet resistance. And we're going to use Irwin's curves to do this. So let's look on slide number 9. So these are the constraints for, again, repeated. The sheet resistance is 900 ohms per square. The junction depth has to be 3 microns. And the background concentration, either NB or substrate concentration, maybe you write NBC, is 10 to the 15th. So given the requirements that we have been told, I can actually immediately find the x-axis on the Irwin curve with the average conductivity layer. It's just 1 over the sheet resistance times xj. So the average conductivity calculates out to be 3.7 ohm centimeter to the -1. We can now, from Irwin's curve, we can obtain, assuming this is the Gaussian, that's assumption we need to make at this point, which we'll show is reasonable later. We can then obtain the surface concentration. So in order for knowing the shape of the Gaussian, basically Irwin's intervals tells us that the surface concentration has to be about 4 times 10 to the 17th per cubic centimeter in order to achieve an average conductivity that has been specified of 3.7, assuming the junction depth is 3 microns. So that's, and if you want to see that, how we actually do that, you can go on to slide number 10, and this actually shows how the curves were used. Again, this is for a P-type Gaussian profile, and all we've done is on the x-axis picked out, it's a little hard because this is a log plot. On the x-axis picked out the average conductivity to be 3.7, and it's a little tricky to find that, but you can, and then you read off the y-axis as shown by that horizontal line, surface concentration about 4 times 10 to the 17th. And again, we have multiple curves we can choose. I choose to use the orange curve, which is for the case of a background concentration, in this example, of 10 to the 15th. If the background concentration, say, had been a little bit higher, say 10 to the 16th or 10 to the 17th, what you see would have happened is that the surface concentration would have actually moved down a little bit on the y-axis. So it would intersect a slightly different curve. Okay, so that's how we come up with the surface concentration. So let's go on to slide 11. And thinking about that surface concentration, C sub S, we know it's well below the solid solubility of boron and silicon. It's only 4 10 to the 17th. And it's probably likely below the value of N sub I at the diffusion temperature. Again, at 1,000 degrees, which is probably somewhere near or a minimum temperature you'll be using to drive this in, N sub I is about mid 10 to the 18th. And so mid 10 to the 17th is well below that. So it's probably valid then to say that the profile is Gaussian. It's probably valid to say that it is a constant diffusivity D. And therefore we can assume this Gaussian type of solution because it's a drive-in. So we can write down sort of by inspection the equation in the center of the slide, which is the Gaussian equation. And then we know that at the point where x equals xj, the carrier concentration or the doping concentration, C of the boron, reaches that of the background. That's the definition of xj. So if you look in the middle of the slide, we're saying the background background concentration, CBC, is equal to the surface concentration, C sub S, which we just located, we just found, times exponential of the minus xj squared over 4 dt. That's the definition of xj. So we know xj in this equation, which is found C sub S. We know the background doping concentration. The only thing we don't know is dt, so we can invert that equation and solve for dt. Plug in all the numbers, and you get a dt product in order to obtain this Gaussian of 3.7 times 10 to the minus 9 centimeters squared. And that's the dt product, the so-called, if you would like to use the term, thermal budget for the drive-in process. So that gives us an idea. And we don't know what D is or what T is, but we're going to design a certain temperature and time. So we constrain to the fact that the dt product will be this number. So let's go on to slide number 12. And again, I'm repeating the dt product from the top, 3.9 times 10 to the minus 9, 3.7. Let's just assume a temperature and see what happens, see what time is associated with that, and if it's a reasonable amount of time. So let's say we know we're diffusing pretty deep down to 3 microns. So let's just say we assume we drive in at 1100 degrees centigrade. And then you can look up from your plots, or you can calculate the diffusivity of boron at 1100. It's about 1.5 times 10 to the minus 13 centimeters squared per second. And so then you can solve for time. The drive-in time, calculate that out, you get about 6.7 hours. It's plenty long. That tells you probably from a practical point of view, you would not want to do this drive-in any lower temperature because it would just take too darn long. Okay, so now one thing we'd like to calculate, we have figured out the surface concentration from Irwin's curves, and we have the dt product. It will be interesting to calculate the initial dose, or the dose, the area under the curve for the Gaussian profile. We have everything we need. Again, we know the dose Q is the surface concentration, C sub S times the square root of pi dt. And we have all those quantities. We can plug them in, and we get Q equal to 4.3 times 10 to the 13th. That's the interval under the Gaussian. It's a relatively low dose compared to implant range, so it can be implanted. So this dose can easily be implanted into a very narrow layer close to the surface, which justifies implicitly, because that narrow layer might only be 1,000 angstroms deep. It justifies our implicit assumption in using a Gaussian profile that the initial distribution would be a delta function. maybe only, again, a few thousand angstroms deep, and you're going to a final junction depth that is 3 microns. And certainly that seems justified using the Gaussian profile. Okay, let's go on to slide number 13. And now that was the case we just talked about, assuming we had implanted the dose. Let's just take the case where if we used gas phase pre-depth step as an example to get the boron initially into the wafer, and say that was done at 950. You can then use the charts in your book or in the handouts to look up the solubility of boron at 950, and you'll see it's pretty high. It's 2.5 10 to the 20. And at that temperature, then we can also look up the diffusivity. It's about 4 10 to the minus 15th. So you can solve for the dose in the complementary error function profile, Q. You have everything you need in that equation, 2 C sub S over square root of pi square root of dt. And so the time that you would require to deposit that dose into the wafer, T of the pre-depth, can be solved, and you find about 5.5 seconds. So you now see that the dt product of the pre-depth, which you can calculate as 5.5 seconds times the diffusivity at 950, which we see from above is 4 10 to the minus 15th. So that dt pre-depth is about 2 times 10 to the minus 14th. And comparing that to the dt of the drive-in, which we solved for earlier, which is about 1.5 times 10 to the minus 13th. So, order of magnitude difference there. Again, this tells us that the assumption of Gaussian diffusion is justified, even if we had done a solid phase pre-depth. Okay, so that's the end of slide 13. That sort of gives you an idea of how these Irwin curves can be used to design a process. The alternative you could use them is to read off. If you go back to just momentarily slide 10, the problem might be specified differently. You might be given, some kind of surface concentration and background concentration, and have to back out what the effective conductivity of the layer might be. So, different ways of getting those curves. So let's go on now to slide number 14. And I want to shift gears a little bit because we have more or less covered a few cases for which the analytic solutions can be obtained. And those are important cases, but primarily when the dopant concentration is low or satisfying certain special conditions, like during pre-depths. It'll turn out there's most cases we cannot solve analytically. So these solutions have to be obtained by using computers using numerical methods. And so I wanted to introduce you in the next few slides to some of the simplest types of numerical methods, so you have an idea or a feel for how you yourself could implement these numerical techniques if you need to do it. And there are textbooks on this topic. In particular, if you want to look at more detailed information on numerical solutions of diffusion equation, there's a book by J. Crank called The Mathematics of Diffusion, has a chapter on numerical methods for this particular equation. The nice thing about numerical methods, they can be used to solve arbitrary initial starting profiles. So you don't have to make any detailed assumptions, arbitrary boundary conditions, and in the case where the diffusivity varies in space. So if you have a concentration-dependent diffusivity, which will be the case we'll talk about in later lectures when the dopant concentration is quite high, and you can use numerical methods. So what I'm picturing here on slide number 14 is a very schematic picture of atoms moving around between planes in a lattice. And so let's use this picture to get some physical insight into the diffusion process. So each plane here is sort of indicated by a vertical bar, and 0, 1, 2, 3, 4. And the distance between these planes is given by the distance delta x, so as units of length. And n sub I here, so n0, n1, and 2, is the planar atomic density of the ith plane. So it's the number of atoms per square centimeter in a given plane. And C sub I has volume concentration units. It's the average volume concentration at any point. So you can calculate, you can get between the two. C sub I is just n sub I over delta x, or n sub I is just C sub I times delta x. Okay, so let's go on to slide 15, where at the top I've just reproduced that picture, so a smaller version of it, and just reminding ourselves of the relationship between Ci and Ni. Now, as we're looking at this lattice, we know that the atoms are relatively fixed in the lattice, but they do vibrate about their average position in a plane, their average position, and they're vibrating at some frequency, V sub d, which is called the Debye frequency. And that number is typically on the order of about 10 to the 13th per second. So it's a pretty high frequency. They're vibrating about their average lattice positions at a finite temperature. Now, sometimes during this vibration, an atom will actually be able to surmount the energy barrier that exists in going from one lattice position to the next, or one plane to the next. And it will actually be able to hop to an adjacent plane. And there's an energy barrier, which we'll call an E sub b, to get from one plane to the next. And this hopping frequency we call V sub b, which is just the Debye frequency, Vd, that's the vibration frequency, times a Boltzmann factor, exponential the minus Eb, that's the energy barrier, over kT. So this V sub b, small v sub b, gives us an idea of the frequency of hopping from atoms from one plane to the next. And what we assume in this derivation is that there's equal probability of jumping right or left, because this is a random process. So if we look at any given plane, we can say the number of atoms jumping to the right of that plane per unit time is just VB over 2 times the number of atoms in that plane, n. Half of them go right. Number jumping left per unit time is just VB over 2 times the number in the plane, n. Those two are equal. Now, if we do the bookkeeping and say, look at the number of atoms crossing a plane, the particular plane at I equals 2 in the above diagram. So the plane labeled 2. The number of atoms crossing that plane per unit time, well, we can just write that as a flux. And F, an equation on the bottom, well, that's just going to be the number of atoms, basically per unit time, jumping to the right minus those jumping to the left. So you write that as V minus VB over 2, N2 minus N1. Again, assuming equal probability going either way. And then you can convert that, the difference between atomic density and number of atoms per cubic centimeter, just by multiplying, using the definition of N is equal to delta X times the concentration. You have then an expression for this flux, crossing plane I equals 2. And then you multiply and divide by delta X, and you end up with this equation that this flux is equal to, looking on the right-hand side, minus VB over 2 delta X squared times the delta C over delta X, something that's starting to look like a slope. So we immediately see some kind of fixed law here, where a flux is related to a slope times something out in front that is a constant. So that's at the bottom of slide 15. Let's go on to slide 16. And I've just repeated that equation that we just had, but I added one more thing on the right, one more equality, and we set that flux equal to a diffusivity, a number d, times the slope, delta c over delta x, where we define the diffusivity in this particular equation to be equal to the VB over 2 times delta x squared. So there is fixed first law. The flux is equal to minus a diffusivity, a constant number, times delta c over delta x. And the diffusivity has some atomic scale mechanisms of view to it. In fact, it's proportional to the jump frequency, V sub b. And therefore proportional, be related to the energy barrier to hop between adjacent positions or adjacent planes. So it gives you some idea of what at the atomic scale, what goes into determining the diffusivity d. Okay, in addition to giving us an atomic scale view, we can actually use this type of formalism to go ahead and derive a numerical solution to fix equations. So let's go on to do that. We'll go on to slide number 17, which is a slightly different sketch, but the exact same ideas of what we'll be going through. And what I'm showing on the left-hand side in the bottom is a plot of concentration as a function of x, so distance. And let's say it has some shape, this dark decreasing black line, and it's decreasing from left to right. And what we're going to do is we're going to discretize this. We're going to look at discrete positions in space, x, and we'll look at the concentration C0, C1, and C2. And the spacing between those planes is going to be a constant, just like we used before, delta x. And so what we're going to look at is in the time interval delta t, a certain time interval delta t, what is the number of atoms crossing a certain plane per unit area? And we call that, for the plane R, which we have labeled R above, Q sub R. It's just the flux, F sub R, times delta t. That's the number of atoms crossing the unit area in a given time interval. That's just basically, this comes from the definition of what flux is. And we then can write in for the flux. The flux is just the diffusivity d times the concentration difference across that plane. Across plane R, well, the concentration difference across plane R is C1 minus C0 divided by delta x. So we can approximate it that way. The flux crossing plane R. What's the flux crossing plane S? Well, we can do the exact same thing, or the number of atoms crossing plane S. It's just the diffusivity times delta t times this time. We subtract C2 minus C1 over delta x. So we can then do some bookkeeping and calculate the net number of atoms accumulated in that shaded region between plane R and plane S. In the time interval delta t, it's just QR minus QS. And we just subtract these two expressions, and you see what you end up with is equal to a diffusivity d times the time interval delta t times, in parentheses, the C0 minus 2C1 plus C2, that whole thing, quantity, over delta x. Now, if we divide that net gain in the number of atoms divided by delta x as shown below, that is the net gain in the concentration in that shaded region. That's delta C. And that's just QR minus QS, that whole quantity divided by delta x. So I can substituting in QR minus QS, and you end up with the equation near the bottom, which just says the net gain in the concentration, delta C in this shaded region, is just the diffusivity d times delta t times this quantity in parentheses, which is related to the concentrations in those three regions, divided by delta x squared. So what it says is at a given point C1 in this curve, if I know the concentrations at the neighboring points, so I know its neighbors, I know the concentration at C0 and at C2, you can calculate a new concentration after a certain time step, delta t, at C1, just by knowing its neighbors at this time step, the concentration of its neighbors. So if we go on to slide number 18, we can then use that information to come up with something called an explicit finite difference formula. And that's what the equation being shown near the top of slide 18. What you're saying is that the concentration at any given point I in one of these slabs at a new time, t plus delta t. So we're going to evolve this profile over time. So C sub I plus on the left-hand side is equal to the concentration at time t. So at one interval before that, whatever it was before, plus we add in this difference, this term on the right. That gives the change in the concentration in the ith slab after a time step delta t. And that term is just d, the diffusivity, delta t divided by delta x squared times the quantity in parentheses. Where again, the quantity in parentheses, in order to evaluate it at any point ci, all I need to know is the concentration at that point and the concentration of its two nearest neighbors. In whatever way that we've discretized, assuming we've discretized this continuous function into little intervals delta x. So that is an explicit formula you can use to evolve a concentration profile in shape over time. And if you look at it for a few minutes, you can notice the similarity of that difference formula to the differential equation for diffusion. which if you take the partial chi on this equation shown in the center and move it over to the right-hand side, you can see that partial c is equal to some constant d times a second derivative of concentration with respect to x. And in fact, this partial second derivative c with respect to x, it can be numerically evaluated as the term in the first equation on slide 18 on the right-hand side. That is a numerical solution to that differential equation. And I won't derive it here. If you go back to Crank's book or any of the books on numerical methods, and you find that the method is numerically stable. So it works from a numerical point of view. It gives reasonable answers for a particular condition. When we're doing this solution, we have a condition on a quantity r, where this quantity r is what multiplies the concentration change in a slab at a certain time step delta t, that d delta t over delta x squared, that multiplier has to be less than or equal to 1/2. If that multiplier gets too large, the whole method breaks down, becomes unstable, and you get nonsense, absolutely totally unmeaningful solutions. So you need to adjust, if you're doing this numerical, make sure you adjust your time steps delta t to be small enough so that this holds, and your delta x to be of appropriate size with respect to delta t, so that you don't get yourself out of the physically out of the numerically stable solution. It's a very powerful technique. It's very simple. That's one of the nice things about it. And it's certainly going to be required to use some method, numerical method, when the diffusivity is not a constant. If you were to sit down, you could write your own simple simulator using this very relatively easy to use finite difference formula. It is not the particular type of numerical method that is being used in Supreme 4. Supreme 4 has a more sophisticated numerical solution method for the diffusion equation. This is much more simplified, and this particular method can be slow. It has all of its own problems, but the beauty of it is the simplicity. And just to give you an idea of how one might use numerical solutions to obtain numerical methods to obtain solutions of the diffusion equation. Okay, let's go on now to slide number 19. What I want to talk about at this point are, from now on, and this is the rest of this lecture and the next couple of lectures, will be the so-called modifications of Fick's laws. Fick's laws are introduced in a lot of basic courses, material science or physics, and when we are diffusing dopants in semiconductors in practical cases, there are a number of cases where Fick's laws need to be modified to take into account the things that are really going on in semiconductor processing. And the first thing that we'll talk about here on slide 19 is so-called electric field effect. And this occurs in the case when the doping concentration is higher than N sub I. So N sub I is the intrinsic carrier concentration at a diffusion temperature, again, of 1,000. N sub I is close to mid 10 to the 18th or so. If the doping concentration gets higher than that, you can start to have a non-uniformity in the charge distribution of the semiconductor, and electric field effects can become important. And this is a schematic demonstration of how electric fields can arise when dopants are diffusing in silicon. And there's a plot of concentration schematically versus depth, and the red line is supposed to represent the profile at any given point in time for, say, arsenic that's diffusing. And arsenic is a donor. It has one extra electron floating around it. But the atom itself, in the absence of this electron, this extra valence electron, the donor itself is positively charged. It's an ion. This arsenic is diffusing, and there are the electrons associated with this heavily doped arsenic region can diffuse ahead of the dopant. And so this blue line is meant to represent the distribution or the diffusion profile of electrons, let's say. So the electrons diffuse, and holes diffuse more rapidly than their associated donors and acceptors. Because of that more rapid diffusion, they'll diffuse the profile for electrons will be a little bit deeper. They'll diffuse sort of ahead of the dopant that they're associated with until they reach some steady state condition where the drift flux from the internal electric field is going to balance the diffusion flux. And so what we look at here is if you just look at this schematic picture, you'll see there is indeed, from your elementary electronics or solid state physics, there is an electric field induced by this, the fact that there's a net positive charge on the left region. That is, if you subtract all the arsenic donors, you subtract the electron concentration there's a net positive charge on the left. There's a little bit of net negative charge on the right that produces an electric field pointing from left to right. So that electric field then tends to cause electrons to drift from right to left, right? Because they drift against the field. So they're going to be drifting from right to left while they're diffusing from left to right because there's a concentration gradient. So the electric field will build up to the point where there's steady state, where that drift flux just balances the diffusion flux for the electrons. And again, the physical origin of this electric field is the fact that, well, electrons are charged in holes, and they have somewhat higher mobility. They can move around the lattice much more readily than the dopant ions themselves. Okay, and again, this is only going to happen in a particular case where the concentration of the dopant is higher than N sub I. Otherwise, the background electron concentration is set by the temperature. It's just a constant throughout space. So the electric field would not develop right at the edge of this diffusion profile. Let's go on to slide number 20. And so what we do is we modify Fick's first law, and we modify it in a way that's very similar and pretty much almost identical to what we do in our electronics or solid state physics classes. We say that the total impurity atom flux in the presence of both a concentration gradient and an electric field can be written down as the sum of two fluxes. One is F, which is the normal Fickian diffusion flux, which is given by minus D, partial C, partial X, plus F prime, where F prime is now the drift flux due to the electric field. And for the drift flux, I wrote down Z, which is the charge number. Z would be 1, for electron, depends on the number of electronic charges associated with whatever is drifting, times the mobility mu, times the concentration C, times the electric field. That is the flux due to drift. Again, that's not a diffusion process, that's a drift process. It's a different physical process. And you're going to add these two together. Now write that as the total flux. So we have a non-Fickian term on the right. But because of the Einstein relation, we can actually, when we're talking about the diffusion of carriers like electrons and holes, we know that their mobility is directly proportional to the diffusivity, and the proportionality constant is Q over KT. So mu is equal to D times Q over KT. So we can substitute in for the mobility in the upper right hand equation with a substitute in Q over KT times D. We can also substitute in the fact that electric field E is the gradient of the potential, where the potential psi can be related to the carrier concentration N as minus KT over Q times the ln of N over Ni. So basically, by substituting in the expression proportional diffusivity for mu, and substituting in for the electric field, how it relates to the potential, and therefore to N over Ni, we get the equation near the bottom for the flux F. It's just the usual Fickian minus D times partial C partial X times minus D times the concentration C times, now we've come up with this psi term, partial X of the potential then N over Ni. So now this is the new flux equation, and we use for the carrier concentration N. You have to be careful; it's not just equal to ND, because Ni can be of order Nd in this, so we need to make sure we use the full expression for the carrier concentration, and it's 1/2 this, the bottom equation here is 1/2 times the quantity, square root of Nd squared plus 4Ni squared plus Nd. That comes from charge neutrality. Given that therefore there's a relationship between N, the carrier concentration, and the concentration of the dopant C, because again, the concentration C is just Nd minus Na. So it's the net concentration. So we have a relationship between N and C. We're going to use that to make this flux equation F to be written only in terms of the concentration C. So we go on to the next page, slide 21. What we find is that we can do this compression of this equation, and we find that the total flux now, F, is written as something called minus H times the diffusivity of a dopant, D sub A, partial C, partial X. So we've been able to actually write down an equation that looks just like Fick's first law, but there's an H factor multiplying it. And this H factor turns out to be equal to 1 plus C divided by the quantity square root of C squared plus 4Ni squared. So basically, it looks this in the presence of an electric field, it looks just like we have an enhancement in the diffusivity of the dopant by a factor called H. We just worked that out. So interestingly, we see that electric field effect on a dopant that is creating the field, on that dopant itself, it enhances the diffusivity, and it turns out H has an upper bound of 2. So H is not going to be any larger than 2, and that means that the electric field enhancement term can enhance the diffusivity of the dopant that causes the field by as much as, or a maximum of a factor of 2. And this happens when the dopant concentration term, or when C, is much, much greater than Ni. And you can see that by substituting in and calculating out what H is in certain conditions. When in the special case where C is Ni, then H goes back to being equal to 1. So how do we get to this equation where this simplified H factor? Well, if you go on onto slide number 22, actually I'm not going to go through all the algebra, but basically what we did was we used a particular fact, which is that on the top of slide 22, partial x of the logarithm of x is equal to 1 over x. And what we needed to find in that earlier diffusion, and that earlier drift term, there was a term that went partial x of ln of n over ni. And so just by going through the algebra shown on we can substitute on slide 22, we can substitute for the carrier concentration N, and we can find an expression for partial x of ln of n over ni. And you see that in the middle of the slide, and then we substitute in that the dopant concentration Nd is equal to C. And we're able to see then that the total flux is the usual Fickian term, D minus D times partial C partial X, minus this other term, which ends up being able to be written just like partial C partial X in terms of partial C partial X times the H factor, where H is equal to, as it's shown on the bottom, 1 plus C over the square root of C squared plus 4Ni squared. So that just justifies the derivation of the H factor on slide 22. Okay, so just go back to slide 21 for 1 second and just want to remind ourselves that the total flux F now in the presence of a high carrier concentration can be written just like the Fickian diffusion, but the H, there's a multiplier H from the diffusivity of the dopant, atom A. Let's skip on to slide 23 now. However, so that's when we were talking about the amount of enhancement you might get in the high concentration species. But you may have 2 different species diffusing. And in the case where the species are at different concentrations, the electric field term can actually cause an even larger change in the diffusivity of the low concentration dopant. So let's look at a particular example shown on slide 23. And what we're showing here is concentration as a function of depth. And the red curve in high concentration, let's say the high concentration arsenic profile. The initial arsenic profile it was ion implanted or something, it looks like this, as shown in the solid red curve. The background doping is initially all constant. It's p-type, so just boron is shown by the solid blue line. Now we're going to simulate, including electric field effects, at 1,000 degrees, the diffusion of the arsenic and the boron. Well, it turns out the arsenic does indeed diffuse, as shown by the dashed line, but that the electric field that it produces right near its the slope, right near the edge of its profile, actually that electric field can cause a flux of boron ions, which can cause the boron to itself to move. So the final boron profile now is shown by the blue dash line, has this little hump in it and then a dip, and that little dip occurs right near where the junction is, right near where the arsenic and the boron cross. And there's no way by Fickian diffusion you would ever predict that a constant profile of boron would end up looking the way it does in this particular plot. Again, that's because of the second term, the electric field term, that non-Fickian term. So, and when you want to think about that, how that occurred, look at the electric field arrow drawn from left to right. Again, drawing from net positive and net negative charge. That direction of E pulls the boron. Again, remember the boron ions, as they diffuse, they're B minus, these acceptors, net negative charge. So they're going to be pulled in. They're going to move to the left by the electric field. They'll be pulled into the N plus region and deplete some of the boron in the region past the junction. And so you end up with this sort of hump and dip, which is a non-Fickian type of motion, but induced by the electric field created by the higher concentration arsenic species. So this can have quite a bit of an effect on the diffusion profiles near a junction, and we see this all the time in our devices. In fact, you go on to slide number 23, showing a simulation example of an N MOSFET. These are two supreme simulations, both found at 1,000 degrees. For MOSFETs, you'll recognize the polysilicon gate here in magenta. And the source and drains regions are arsenic, and they are shown in black. If you look first at the left, in the case of no electric field, you see these different contours, the green, yellow, sort of light orange, and then dark orange or red. We see the boron sort of uniformly doped, and its contours are shown by the different colors. And now what happens on the right, in the presence of an electric field, instead of these sort of uniform lateral doping contours for the boron, you see there's a electric field that sort of acts on the boron and really changes the dopant distribution and its shape. In fact, it dominates the shape of the boron distribution, particularly near the source-drain junctions of a MOSFET device. The boron basically gets pulled in to underneath the source and drains, and there's quite a bit of loss of boron from the channel region into the source drains. That due to the electric field effect, that's not predicted on the left-hand side. So even though the H factor, the enhancement in the arsenic diffusivity, is limited to at most a factor of 2, so there's not too much effect on the junction of the arsenic. You can see the black junctions, those regions don't change that significantly, but it dominates the diffusion of the boron underneath, or at a lower concentration. So let's go on to slide number 25. I just want to summarize this second lecture on diffusion. We reviewed a few cases of simple constant diffusivity. These generally apply well to the case of low doping concentrations in a CMOS process flow. That usually means the diffusion of the CMOS wells, which are fairly lightly doped, say below mid 10 to the 17th or below 10 to the 18th. They're usually diffused in at very high temperatures, so N sub I is large, and they satisfy the fact that the dopant concentration is less than Ni, so you have constant diffusivities. But beyond that case, it turns out most diffusion problems in devices need to be solved numerically, and we introduced a very simple but powerful method for a numerical solution to the diffusion equation, and it actually was a finite difference formula. It's not that that sophisticated, and it's not actually the formulation that is using Supreme 4, but it gives you an idea if you needed to write your own simple method. We talked about the first type of modification we need to make to fix first law, and that was for electric field effects, which can enhance the diffusivity of a high concentration species up to a factor of 2, but can dramatically impact the motion of species at lower concentrations. And what we're going to talk about next time are further sort of corrections to the simple Ficking diffusion that we've been talking about, and more realistic doping profiles, such as the case when we have concentration-dependent diffusivity. Okay, that's all I have for today, and thanks very much.